In this video, we're going to continue to talk about vaporization and condensation, and we begin with the idea of dynamic equilibrium. So if you have a liquid in a closed container, what's going to happen is that liquid will start to vaporize, and some of the vapor will form back into the liquid for condensation. Let me change my pointer here. Pick the wrong one. So change from vapor back into liquid, which is condensation. And eventually, these rates will be the same, and that's called dynamic equilibrium. So when you start, as soon as you seal that solution, liquid's going to evaporate much faster than it condenses because there's no vapor to condense. As you get more vapor, then the higher chance of that vapor hitting the liquid and condensing. And eventually, your rate of evaporation and your rate of condensation will be exactly the same. And that's what we call dynamic equilibrium. And note, at equilibrium, you still have liquid forming vapor. You still have vapor forming liquid. So you still have the reaction going. They're just going at the same exact rate. Right? Now, if we're in a closed container, the pressure exerted by the vapor is what we call vapor pressure. And you probably heard this term if you've looked up the weather, vapor pressure, right? And this has to do with intermolecular forces. So the weaker your intermolecular forces are, the more likely you're going to be in the vapor, so the more molecules you'll be in the vapor. Therefore, if you have weak intermolecular forces, you'll have higher vapor pressure. And the higher the vapor pressure, the more volatile your liquid is. Right? So let's say that you're in a chamber and you can increase the volume of this chamber while still keeping it closed. What's going to happen is that you'll instantaneously decrease the vapor pressure because there's less vapor molecules in an area. So you keep the vapor molecules the same number, but you increase the area. That decreases the pressure, right? So that will mean you have just increased the volume, so your rate of vaporization will increase, and this will be faster than your rate of condensation. And this will in turn increase the amount of vapor. But eventually, in this new volume, you'll have enough vapor in there that eventually your dynamic equilibrium will be reestablished, and the rates of vaporization and the rate of condensation will be the same again. But at this point, what is interesting is that even though you have increased the volume, eventually the vapor pressure of this new volume will be the same as the vapor pressure of your old volume. Right? So let's take a look at this. So in picture A, we have dynamic equilibrium established. Vaporization and condensation rates are the same. If we have a piston and we move that piston up, we increase the volume, so vapor has more places to go, so the rate of condensation will decrease, and your rate of vaporization will be the same as it was. Effectively, more molecules will vaporize until you reestablish equilibrium. While if you decrease the volume by closing in the piston, there's less volume for your gas to go. Therefore, they are more likely to hit the water, so your rate of condensation will increase until you eventually regain this dynamic equilibrium, and your vapor pressure will be the same as it was in A. Now, vapor pressure is very temperature dependent. Again, we know this from our weather. The hotter it is, the greater the vapor pressure is. And it really doesn't matter what type of molecule we look at. All molecules will have an increase in vapor pressure with temperature. And here at 760 torr, which is 1 atmosphere, this is the boiling point. So for diethyl ether, it's 34.6, and for water, we know it's 100. So increasing temperature give your liquid molecules more kinetic energy, and the more likely they are to escape, which increases the vapor pressure. And let's talk about this idea of boiling point now. If you add enough energy into your liquid or enough heat, eventually the vapor pressure is the same as the atmospheric pressure. What that means is that your vapor bubbles will form anywhere in the liquid now, just not on the surface. It will form anywhere, and we call this boiling, as shown with this jug of water. And since pressure, atmospheric pressure, is dependent on elevation, that means boiling point is also dependent on elevation. So if you're on Mount Everest, the atmospheric pressure is only a third of what it is at sea level, and so boiling point of water is only 78 degrees. While at sea level, the pressure is 1 atmosphere, so here our vapor pressure is our boiling point is 100 degrees centigrade. And the way to really think about this is that the pressure of the atmosphere is pushing against that liquid, so it takes more energy to boil. Now let's look at what a heating curve of a liquid. And we learned back in Gen Chem 1 that to heat up a substance, we use this equation where heat, which is Q, equals the mass of our substance times the heat capacity of our substance, Cs, times our change in temperature. So this is water. So what happens with water is as we add heat, the temperature of that liquid water will start to increase until we hit the boiling point. At 100 degrees, water will never go above 100 degrees if it's pure water. Instead, all the energy that is being added to water at 100 degrees is going into breaking your hydrogen bonds, your intermolecular forces, turning all that liquid water into gas, till eventually all your liquid is gas, and then you can use that energy, your heat, to heat up the gas. So liquid water will never be over 100, and it will never be below 0 for the same type of idea. All that energy is going into boiling the water at 100 degrees centigrade. And we have an equation to understand this idea, the Clausius-Clapeyron equation. And the Clausius-Clapeyron plot is you take your pressure, your vapor pressure, and you take the natural log of your vapor pressure. You plot that on the y-axis. Then you have the temperature plotted on the x-axis, but it's inverse temperature, 1 over T. And so what you do is you take your liquid, which is at various different temperatures, and you just measure the vapor pressure, and you plot that on this plot, and then you make a line from that plot. The slope of your line is delta H vaporization divided by a constant, which our constant is the gas constant, which is 8.314. So with just vapor pressure and just temperature, you can tell how much energy you need to put into a liquid to turn 1 mole of liquid into a gas. And we also have a 2-point form of this equation. That is, if you only have 2 vapor pressures and 2 temperatures, you can still figure out what delta H vaporization is. Now, it's less accurate than doing the whole plot, but it is easier. And we should already have 1 point if we're dealing with water, because water's at atmosphere 760 torr, water boils at 100 degrees centigrade. So as long as we have a second pressure and a second temperature, we can tell delta H vaporization, or the amount of energy we need to vaporize 1 mole of water, from that data point. Okay, the last thing we're going to talk about in this section are critical fluids. And a critical fluid is a fluid that has properties of both a gas and a liquid, but it is not a gas or a liquid. And to get this supercritical fluid, we have to be at a certain temperature and a certain pressure. So at this certain temperature and certain pressure, we call that the critical temperature and the critical pressure. So at this temperature, the gas cannot be put into a liquid no matter what the pressure is. And so here we have a liquid. And right now the liquid is in dynamic equilibrium with its gas. So we have liquid and a gas. And this is a closed container. And eventually we're going to increase the temperature of this liquid, turning more and more to vapor until your separation disappears and you have a supercritical fluid. You have something that has properties of a gas and a liquid, but is neither a gas and a liquid. A very, very odd state of matter, but it can exist. And we call those supercritical fluids. And that is the end of this section. I will see you in the next video.